Hey kiddos, happy week 18. This is our last lesson for semester 1. So today we're going to describe the effect of perceived frequency when there is relative motion between a sound source and an observer. We're then going to calculate the velocity of the sound source or observer using the Doppler effect equations. Okay, so in this unit, waves, simple harmonic motion, and sound. This is the last unit, and we're looking at the Doppler effect. So that woo sound, right, when a siren is going by. Okay, so let's take a look at a scenario. And I just want you to describe from your experience as a person living in the world, if you were to stand on the sidewalk as a fire truck with its sirens blaring speeds by, what would you hear? Okay, what would the pitch of the sound sound like as the truck approached you and as the truck moves away from you? Okay, take a moment to respond, maybe even pause the video. Okay, so most of us have experienced this. As the truck approaches you, the perceived sound is high pitched. And it's got a high note associated with it. And when we're talking about sound, high pitches are a result of a high frequency, low wavelength. Okay, high frequency sounds or high frequency waves have a low wavelength. As the truck moves away from you, the sound is more low pitched. Right, which means it's got a low frequency. High wavelength. Okay, so the waves are spread further apart when the truck moves away from us. Okay, just as a reminder, the sound that we're hearing is traveling through the air. The speed of any wave is determined by its by the medium that it's traveling through. So the speed of sound isn't going to change because the sound is always moving through air. Right? But if the frequency changes, if the frequency goes up, the wavelength must go down to maintain that constant wave speed. Okay, so again, siren goes by, woo, right? That sound is the Doppler effect. So as it approaches high frequency, a high note, which is associated with a low or a small wavelength, the waves are close together. As the truck moves away, it's low pitched as a low frequency, which means the waves are happening less often, and there is a high or a large wavelength, which means the waves are further apart. This is just based on our experience and some basic understanding of waves. Now, why does this happen? Here's a little graphic here showing if you were standing on the sidewalk and a truck is at rest, sitting still, running its sirens, you would perceive a constant pitch, right? There would be no perceived change in the pitch of the siren sound as a result of the truck's motion. So what you're seeing here is pointing out over here the circular lines that are drawn. They're calling them condensations here. Excuse me. Previously, we've called those compressions. Right, high pressure regions of a sound wave, and so this is these lines also visually are called wave fronts. Sorry, I was distracted by a giant noisy truck going by my house. Okay, so each of these lines are called wave fronts. And what you're noticing here is between each wave front, right, the distance in between these visual wave fronts is a wavelength. Okay, so you can see that there's a constant wavelength in between each of these wave fronts. All right, but when the truck is moving, and there are two observers here, right? And with the truck at rest, the two observers would be perceiving sound that is at the same wavelength, right? But this observer right here, when the truck is moving away, it will perceive a larger wavelength. And when the truck is moving towards this observer here, they will perceive a smaller wavelength of sound. Why is that? And that's what we're going to dig into today. So the Doppler effect is the phenomena in which there is a change in frequency or pitch of a sound detected by an observer because the sound source and the observer have different velocities with respect to the medium of the sound propagation. Okay, I took a screenshot from a simulation that I was playing around with earlier, and it conveniently shows like a police car moving to the right, right? And we would call that the source of the sound. So the speed of the source would be to the right. It also shows the wave fronts as circles. And in between the wave fronts, it shows the waves themselves. Now it's showing a transverse wave to represent sound. Remember, sound is a longitudinal wave, right? Where the wave fronts are represented by, or represent high compression regions. But this is representing them as a longitudinal wave kind of gives us a visual for frequency and wavelength. Okay, so we see as the car is headed forward, all of the sound waves that are in front of it are compressed, while all of the sound waves that are behind it are stretched. And that's a visualization that we've got. I actually want to pop over to another simulation. Let's take a look at this. Okay, this is an O physics interactive. It's showing the same thing, right? The source is sending out sound waves with a consistent frequency. But the back observer and the front observer, when the source is in between, they're experiencing two different frequencies of sound. There's one more here. It's a gizmo sending out a constant frequency of sound. The observer's little head lights up when they receive sound, like when they hit a compression region. Okay, and it gives the observed frequency. Let's try that one more time. Right, the frequency that the sound is emitted is constant, but we notice the perceived frequency of the observer went from like 600 hertz to 380 something hertz. Okay, and that's actually because the car is moving in the direction of the sound waves. It's actually as it's releasing a sound wave, it's moving towards the wavefront, right? It's moving towards the wavefront that it just released and moving towards away from the other end. So let's actually take the source and we'll speed them up, turn it into an airplane. Let's do that again. Right, as you go faster, the wave fronts in front of the source are much more compressed. Okay, and both of these visualizations are attached to Canvas today for you to take a look at. Okay, I'm going to pause that and go back here. Okay, so let's take a look at some notation. Quickly, it's important to understand this notation and have it copied in your notes for reference. There's also some standard notation and comparison to notation in your IB Physics data booklet. All right, we're going to describe what we saw in equation form. Okay, so our notation, lambda is the actual emitted wavelength. Okay, lambda prime is the wavelength that is observed by the observer. Okay, V sub s is the speed of the source. In your data booklet, it's abbreviated as U sub s. Okay, and then speed of sound or of light, depending on the situation, is V, just plain old V, or C, you'll see sometimes. The speed of the observer, sometimes the observer might be moving instead, and the Doppler effect is as a result of the motion of the observer. It's V sub O or U sub O. Okay, and then F is the actual emitted frequency. F prime or F sub O are the observed frequency. Okay, so a lot of different notation, and it's important, like, depending on the resource that you're using, to kind of be able to switch between those notations.